In this session on Oracle Machine Learning for R, an introduction, we'll discuss some of the issues with traditional R and data source integration, give a brief overview of the Oracle Machine Learning product family, and then focus on features and functionality of Oracle Machine Learning for R, along with a demonstration of Oracle Autonomous Database. OML for R was first released in 2011 for Oracle Database, and new in this release is OML for R version 2.0 for Autonomous Database. My name is Mark Hornick with Oracle Machine Learning Product Management. So here's a quick summary of OML for R capabilities on Autonomous Database. We're able to leverage Autonomous Database as a high-performance computing environment for data exploration and preparation, access in-database machine learning algorithms from an R interface, run user-defined R functions in database spawned and managed R engines, while also storing R objects in the database. Use OML for R from OML notebooks using the Oracle R distribution 405, Oracle's redistribution of open source R. Users can now run R, SQL, and Python paragraphs in the same notebook, selecting the most appropriate language for a given task. Coming soon, we'll be providing a standalone client for access from third-party IDEs like RStudio, as well as the ability to specify additional third-party packages. For our agenda, we'll begin with enterprise machine learning pain points and give a brief overview of Oracle Machine Learning. We'll introduce OML for R, followed by a brief demo. There are a number of pain points enterprise data scientists and other data professionals experience in their machine learning projects. For example, it takes too long to get or load data, or getting models into production takes too long, or it's complex. In other cases, there are concerns about data security, backup, and recovery, where data is pooled into non-secure environments. Yet others will cite scalability and performance as a major concern, both for individual models and when dealing with hundreds or thousands of models in production settings. When talking about separate analytical engines, we might refer to traditional R engine and data source interaction. Analyzing data using open source tools like R and Python, and even proprietary tools, often require enterprise users to request data extracts from data sources, load that flat file data into memory, and then push results back to the data repository. Other users may be able to extract data programmatically through various connectivity packages. For example, on Oracle Database and R, this may be R Oracle. However, it's often problematic for larger data sets given internet bandwidth constraints. Overall, the challenges include data access latency, the need to change language to access or manipulate data, or even more critical, the need for the full data set to reside in memory for analysis. In addition, most third-party packages are single-threaded, meaning that even if you have multiple processors available, scalability and performance will be severely limited. When data is pulled from the database, there are issues of backup, recovery, and security of the data. And for production deployment, there's the need to spawn analytical engines like R, load the data, and enable applications and dashboards to access the results. This all adds up to unnecessary, or at least undesirable, complexity. So this is where Oracle Machine Learning comes in. Oracle Machine Learning is comprised of a family of components supporting data science projects. Oracle Machine Learning enables data exploration and preparation, and model building, evaluation, and deployment at scale. Oracle Machine Learning focuses on interfaces for three popular languages: SQL, R, which is our focus today, and Python. OML for SQL provides a SQL interface to the in-database parallelized algorithms, which keeps data under database control, eliminating the need to extract data to separate machine learning engines. This enables scalability while reducing complexity. The resulting machine learning models, which are first-class database objects, enable batch and real-time scoring directly from SQL queries and provide explanatory prediction details so you can understand why an individual prediction was made. OML for R and OML for Py are R and Python interfaces, respectively. These allow you to manipulate database tables and views using familiar R and Python functions on data frame proxy objects. The in-database algorithms are available through native language interfaces using familiar constructs. They inherit the same benefits of OML for SQL. Also, users can deploy R and Python functions using database spawned and controlled R and Python engines, and do this from SQL and on autonomous database using REST endpoints. For interaction with autonomous database, we provide OML notebooks with SQL, PL/SQL, Python, Markdown, and now R interpreters. The same notebook can contain all of these different paragraphs, allowing users to choose the most effective language for a given task. Oracle Data Miner is a SQL developer extension that enables users to create, schedule, and deploy analytical workflows through a drag and drop user interface. It connects to both Oracle Database and Oracle Autonomous Database instances. OML for Spark provides machine learning in the big data environment, such as Big Data Service using an R interface to scalable parallelized algorithms. Oracle Machine Learning AutoML UI is a no-code user interface that automates the model building, selection, tuning, and deployment process. And lastly, Oracle Machine Learning Services is a RESTful service for model deployment and management, along with cognitive text analytics. Users can deploy models from the AutoML UI directly in OML services in just a few clicks. So let's take a closer look at OML for SQL, the SQL interface for in-database machine learning that provides the foundation for in-database algorithms exposed in OML for R. The in-database parallelized algorithms keep data under database control, as we've said. There's no need to extract data in separate machine learning engines, which can be time-consuming and introduces issues of data security, backup recovery, and even up-to-date data. The algorithms are fast and scalable, enable batch and real-time scoring, and provide explanatory prediction details, so you can understand why an individual prediction is made. In-database machine learning models are also first-class objects in the database. You can control access by granting and revoking permissions, audit user actions, and export and import machine learning models across databases. Since OML for SQL supports the R and Python interfaces, as we've noted a moment ago, OML for R and OML for Py reap the same benefits for in-database models. OML for SQL is at the core of OML's Bring the Algorithms to the Data tagline. So let's move on to OML's interface for open source R. Oracle Machine Learning empowers data scientists with open source R by leveraging the database as a high-performance computing environment. Database tables and views are accessed through data frame proxy objects with overloaded functionality that produces SQL transparently behind the scenes. The in-database machine learning algorithms are exposed through a native R API and produce the same first-class in-database machine learning models as the SQL API. Create user-defined R functions and manage them in the database. Store and manage R objects, like R machine learning models, directly in the database, avoiding the need to manage flat files. Invoke your user-defined R functions from SQL and on autonomous database from REST endpoints. A significant benefit is that deployment doesn't require provisioning separate R engines for solutions. OML for R provides all the infrastructure to automate this. The functionality across OML's R interface is characterized by three functional areas. Using proxy objects, the transparency layer allows users to operate on database data using familiar R syntax, overloading select functions that operate on proxy objects. These functions construct SQL for in-database processing, and results are typically returned as proxy objects themselves for scalability. The in-database algorithms provide scalability and performance and are exposed through convenient R interfaces that leverage the R formula object to specify predictors and targets. And through embedded execution, user-defined R functions can be invoked on database environments spawned and controlled R engines. Embedded execution enables data parallel and task parallel processing. For example, an open source model can be scaled to large volumes of data for making predictions, by requesting that multiple engines be spawned to process chunks of data in parallel. OML provides the supporting infrastructure to simplify and automate this process. For Oracle Database and Database Cloud Service installations, users typically install R and the OML for R server components on each node of the real application cluster server. To use third-party packages with embedded R execution, these must be installed on each node in the cluster as well. On Autonomous Database, of course, OML for R is pre-configured. No installation is necessary. In the coming year, Autonomous Database users will also be able to configure additional third-party packages. So how do we achieve scalability through OML for R? OML for R introduces proxy objects that behave as R data frames, but map to database tables and views. Here we show how the proxy data frame is a subclass of R's data frame class. Note that the structure of the R data frame, which contains the actual data, is very different from the proxy object, which contains a reference or query to the data table or view. This depicts the data query that corresponds to the iris table in the database. To give you a clearer idea of what we mean by the transparency layer, we use proxy objects and overloaded functions to take advantage of database column indexes, query optimization, parallelism, and even table-level partitioning. These can greatly improve performance and scalability on database table operations, since the data is not brought to the client engine. Here we see how we can create a table from an R data frame using ore.create, specifying the table name we wish to use, in this case iris. If the table already exists in the database, we can use the function oresync and specify the table name we wish to access. Each of these returns a proxy object that we can then use to invoke familiar R functions like dim, head, and summary. These overloaded functions, in effect, translate desired functionality to SQL for in-database processing. Just for reference, here's a mapping between R data types and Oracle Database. The OML for R mapping follows that of R Oracle for this processing. For example, if the database has a column of type date or timestamp, this is mapped to R's POSIX-CT data type. If an R data frame has a column of type POSIX-CT or date, this gets written to the database as type timestamp. Here's the set of algorithms supported in OML for R on Autonomous Database. Note that users can also take advantage of automatic data preparation, partitioned model ensembles, and integrated text mining through the same API. Let's take a look at embedded R execution from the R and SQL API's perspective. Here's the code that builds a linear model, storing it in the database using the data store, while having the database spawn and manage an R engine to process it. Our user-defined function, or UDF, builds a model to predict species using a data frame passed as the first argument, and saves the model to the database in a data store using oresave. The return value is simply the Boolean true. Next, create our UDF in the script repository and get a proxy object to the iris table. Then we invoke ORE table apply, providing the proxy object iris, the name of the function in the script repository, the name of the data store under which we'd like to store this model, and to automatically connect to the database from the spawned R engine to access the data store. The database environment spawns an R engine and loads the UDF and iris data from the database. And when finished, we have our model saved in the database and the R engine is released. We can invoke our UDF from SQL, say to allow our application to build this model easily as well. We'll use the rqtableeval database table function. In the first argument to rqtableeval, we specify the source data table name, here iris. We specify the function arguments as a JSON string of name-value pairs, the name of the data store, and that we want to use the Autonomous Database medium service level. We indicate that the output format of the result should be an XML string. Recall, it's just returning true. And lastly, we give the name of our UDF that we just created in the script repository. With the model created and stored in the database, let's define a function that uses that model to make predictions. As before, ORE script create stores the UDF in the database script repository. We can also store our UDF using PL/SQL with the function rqscriptcreate. This allows DBAs or SQL users to receive UDFs from R developers to deploy it themselves, perhaps in secure production systems. So now let's use OML for R to get data parallel behavior using our scoring UDF. After getting a proxy object to the iris table, we provide it to ORE row apply, along with the name of the function in the script repository, and that we want 10 rows to be processed at a time, and to do this in parallel using 4R engines. The fun.value parameter specifies the resulting data frame structure, so it can automatically create a single result as opposed to a list of partial results. Invoking row apply causes the database to spawn the R engines, load the UDF, and a data partition into each of these, and then collect the results, which are presented as a single ORE frame proxy object. Now, this is important since the results themselves can be large. We don't want to pull results to the client unnecessarily. Next, we create the table batch scores and use the overloaded R table function to compute the confusion matrix in the database on the batch scores proxy object. Note that only the confusion matrix itself will be returned to the client without the need to load large volume data to the client R engine. Here's the corresponding SQL invocation using rqroweval on Autonomous Database. We have the data table name iris, our parameter list as a JSON string, which specifies the medium service level, and that parallelism should be enabled. We specify the output format indicating the structure of the result being returned. And in the row num argument, we indicate that 10 rows should be processed at a time in each invocation. And in the source name argument, to use the UDF in the script repository named score data. So let's see a demonstration of OML for R on Autonomous Database using the OML Notebooks interface. We're looking at OML Notebooks on Autonomous Database. For our demonstration of OML for R, we're going to start with the transparency layer. The first thing we need to do is to load the ORE library. ORE stands for Oracle R Enterprise, the original name of this product. Next, we'll create a database table from an R data frame, and we'll get back a proxy object in our R environment. We use the function ORE create to create a table in the database using the iris data frame. After we create this table, we have an ORE frame, and its shape is, as expected, 150 rows and 5 columns. We can list the available objects in our environment by invoking ORE ls. Using the overloaded column names function, we can see the columns of our iris table, as well as the first few rows of the dataset. By using z.show, we're returning the values to be displayed in the Zeppelin notebook environment. We can use the overloaded summary function to compute statistics on the iris dataset in the database, so that no data needs to be retrieved to the client except for the summary statistic values themselves. If desired, we can pull the iris database table data back to our R client, and we'll see that we get back an R data frame. Let's compare the structure of the local iris data frame to that of the ORE frame proxy object. Here we see a very different structure, and one of the key elements is the data query. Here we see the select statement that provides the abstraction over the table in the database. Using standard R syntax, we can select specific columns from our ORE frame proxy object. And we can also use column indexes. This is something you can't do with SQL. We can also exclude columns from a database table. Consider if we had a table with 1,000 columns and we wanted to exclude just one. This is a very convenient way to do that. In SQL, we would have to list the 999 columns that we want to include as opposed to the one we want to exclude. Here are some additional operations that we can perform on filtering rows as well as columns using standard R syntax. Sepal length greater than 5, selecting columns with that, and also more complex specifications. We can use overloaded Dplyr functions to operate on ORE frames. We load the library magrittr as well as ORE Dplyr. In this case, ORE Dplyr needs to be explicitly loaded if you wish to use this functionality. So we can select columns, exclude columns, filter rows, among many other functions provided by the Dplyr package. And here we see the results from that. Now we can join data as well. If we create local data frames and invoke the local R merge function, we can see the result here of the merge. Now we can also create tables in the database using ore.create as we did above. And we can invoke merge on the ORE frames that result from that. And we get the same result, except that it's in reverse order. And that's because row ordering is not automatically enforced due to the expense of computing sorts on data, especially when the data is large. We can also use the Dplyr functionality, here the left join function, to compute the same result. Again, notice the result is not in any specific order. We can store objects in the database data store. In this case, we're going to save the R data frame, iris, in a data store called My Data Store. We'll create a list of a few values, A, B, and C, and we'll save that in the same data store. And then look at the data store that we just created. It shows that we have two objects, the iris data frame and our list, when it was created and its size. We can also see the contents in My Data Store as well. Here we see its iris with the class data frame, and we have the list object, also of class list, with its corresponding size. So let's move on to machine learning. Here we're going to build an in-database random forest model to predict species, and we'll get back a model proxy object. Note that we're using standard R syntax along with the R formula specification. Getting the summary of the model, we see the settings that were used and also the attribute importance ranking of the 4 predictors. We can use this in-database model to make predictions using the model proxy object. We're indicating that we would like not only the final prediction, but also the probability of each of the other classes that could be predicted. We're going to specify the supplemental column species, which is the original target value. We can also compute the confusion matrix in the database using the overloaded table function. And here we see how well the model performed. We can also add our model proxy object to the data store. Now we have 3 objects in My Data Store. We'll wrap up with embedded R execution. We're first going to define an R function to plot n random red dots and return a 2-column data frame. Then we'll run that user-defined function directly in our local R engine. And what we see is that we have the data frame returned along with the plot of the random red dots. Now let's do the same thing using embedded R execution. So we're going to run our user-defined function in a database-spawned R engine, passing the user-defined function along with the argument. We get the same result. Behind the scenes, an R engine was spawned, our random red dots function was passed to it along with the arguments, and the results returned to our client environment. We can also store our user-defined function, random red dots, in the database R script repository. And let's list the script that's there. Here we see that we have its name and the corresponding code for that. We can run our named user-defined function in a database-spawned R engine, passing the function name and the argument. And you see that we get the same result as before. And lastly, we'll illustrate using OML for R supported data parallelism to build one linear model per species. This is using the ORE group apply function, where we pass in our proxy object for iris, the column that we wish to partition the data on, the fact that we want to build one linear model to predict sepal length given the other predictor values, and that we would like to use 2 parallel R engines. This goes off, spawns the multiple R engines, feeding the data to each one as it is processed, and collecting the results. In this case, we see that we have the model for Setosa, for Versicolor, and Virginica. And that's the end of our demonstration. So to summarize, why should you use Oracle Machine Learning with R? I'll highlight a few reasons. OML for R empowers data scientists and broader R users with powerful in-database machine learning from an R API. By running within Oracle Database, users can perform scalable data exploration, data preparation, and machine learning, taking advantage of parallelism and even scoring optimizations at the Oracle Exadata storage tier, while using familiar R syntax and semantics. The integration of Oracle Database with the R open source environment makes it easy for users to deploy machine learning models and custom R scripts from SQL and on autonomous database REST endpoints. This simplifies data science projects and facilitates overall project success. Of course, Oracle Database and Autonomous Database themselves offer a long list of advantages for data management, including security, performance, and scalability. For more information, here are a few resources, including blogs, additional code examples, and documentation. Thanks for joining today's session. You can follow me on Twitter, connect on LinkedIn, and join our Oracle Machine Learning LinkedIn group.